Okay, I'd like to open the afternoon session here. My name is Alan Middleton. I'll be the chair for the session, so I'll be mostly handing around the mic at the end. But I'd like to give a very brief introduction for our speaker today, Irmgard Bischofberger, who is speaking this afternoon. And I won't go into her history too much detail. She had a couple of very prestigious postdocs. She worked at the University of Chicago. She's been a professor at MIT since 2016. And she's done flow of fluids, some very elegant experiments, and a number of fluid flow things, and I think we're going to hear some things related to fluids today. She's also done some very splashy experiments, literally, where she's looked at drops of water falling on things and how drops splash, and I look forward to hearing her talk today.
Thank you very much, Alan. Well, thank you. It's a real pleasure to be here. This is such a fun event for me, so I hope you guys are having fun, and it's really been really good so far. And so what I'd like to do today is to actually take you on a journey through a world of patterns. And so before I actually get into my talk, I'd like to start this with experiments that you're all going to be doing in just a second. So what you're going to be doing is, so you see over there, there's 3 tables. There's these plastic discs on them. And so you're all going to take 2 of them and place one of them on the table, take some of this liquid, place a drop of this liquid onto one of your plates, and then use this second plate to squeeze this droplet of liquid apart. And so when you do that, you want to make sure that you actually have your plates crossed with respect to each other. So like this, and not aligned like this. So keep them crossed. It's going to make it much easier. And so what you're going to be doing is, as I said, you take the second plate, and you essentially press as hard as you can onto this plate. And so far, this is, I admit, quite boring. But I promise it's going to get way more exciting, but I'm not going to show you what you're actually going to be seeing. So I'm trying to take this apart without you seeing. Okay. All right, here we go. And what I want you to do then, once you have your circle, you press down very hard on it, and then you're going to take these 2 plates apart again. In order to do that, that's why you wanted them to be crossed. You can essentially simply press down on the bottom plate and then lift the top plate apart. And try to do that rather quickly, and something miraculous is going to happen. So how about you all get up, go to one of the 3 tables. We'll help you.
Are you going to tell us what the substance is?
I am. I will tell you. Once you have done it, I will reveal all the secrets. All right, so put quite a bit on there. Exactly, this is perfect. And now you press down very hard. Exactly. And now you want to take it apart. Perfect.
Oh, it's a tree of life.
It's a tree of life.
It's a special liquid?
It's a 3D paint, but it pretty much works with any liquid. I'm going to tell you a little bit more about it. Just a second. And
Oh, yes.
okay. Perfect. This came out really nicely. If you can try to tell them to not take too much, I think.
Eric, is it okay if I photograph you?
Sure.
Sorry.
What should we do?
All right, this is pretty good. You can keep it.
They'll dry out.
They'll dry out quickly. So press down. All right. And now lift the top plate. Yep.
Okay.
All right, there you go.
That is cool.
Beautiful.
Yeah, I think one thing is not to use too much liquid.
Yeah.
Doing it as usual. Will this stuff dry out? Or
Yeah, yeah, it will dry out. So if you wait just for 10 minutes, it will be dry.
I'll just leave that here for 15.
Oh, yeah, if you remember which one was yours.
Green and overflowing. Here, there's a couple more over here. I think you're still on.
So it's just fabric paint.
It's fabric paint, yeah. And
There's a couple
but
more
the
setups over here.
That's really
the pattern happens with any liquids, but the fabric paint is nice because it actually dries rather quickly and the pattern remains. And
There's something else to do.
exactly.
Thank you.
Sure.
That's very cool.
Exactly. Yeah, I should maybe point that out.
I'm just going to leave it here for drying.
Sure.
We're using the first one, right? The drying time is 15 minutes.
It's about 15 minutes exactly for this one. Yeah.
Oh, I got your thing. You see it did the
What's that?
little fingers.
I know, that's why I tried to take it away before it happens.
Yeah, okay. The pressure's on. Seriously. Oh, and then you just lift it.
Lift it. Yep.
Oh, very nice. Even I can see this without practicing.
All right. Did everyone get to do one? Awesome. So just before I tell you what's actually happening here, quick. So this is really easy to do. So most of the materials are readily accessible. So what you need is essentially some plastic plates. And McMaster, for example, sells them. Amazon sells them for quite cheap. Then what we used today in the experiment, the liquid you used was what they call a 3D fabric paint, which you can get at Michael's or Amazon. So you'll see that these patterns, they're going to be dry in about 10 to 15 minutes. If you do this with a crowd of small children who don't want to wait 10 to 15 minutes before actually touching it, there's a second way of doing that. You can use Duco cement glue, mix a little bit of food color in it, and then use the Duco cement glue, do the same experiment, and doing that essentially gives you a pattern that dries instantaneously. So whenever I do it with small kids, I actually use the Duco cement because then they can immediately touch it. For you guys, I thought we can handle the 15 minutes. So, but all the materials quite easily accessible and rather cheap. So it's hopefully something you can bring back home. And so what you got from this experiment is a pattern that looks more or less like this, right? You see it has these many branches. If I follow one of these, I see right here it branches into two new ones. It branches again, it branches again, it branches again, which leads to these extremely ramified and complex patterns. And so when you guys did the experiments, I overheard some of you say, oh, this looks just like a tree, or this looks just like a river network. And indeed, these patterns, they have really a large similarity to branching patterns that we see in nature all over the place, where we see them on many different length scales, from very small branching patterns of our blood vessels to like huge scales on, for example, river networks. And so why would nature choose such a structure over and over again? And so one of the reasons is that these branching structures, which essentially grow through these repeated splitting events, they lead to structures that have an extremely large surface area, but a rather small volume. And so maybe the best way to illustrate how powerful of a design protocol this is if you consider our lungs, which are exactly formed by such a branching pattern, where our volume of a pair of our lungs is of the order of about 1 gallon. However, the surface area of our lungs is about 500 to 1,000 square feet. So now, if our lungs wouldn't be this branched structure, but they would essentially be a flat structure, in order to get enough oxygen to the functions of our lungs, we will need a lung that is essentially the size of a tennis court. And so this is really a design that is extremely powerful for many natural systems. And so what I'd like to show you today, or what my research is really driven by, is trying to understand how such very complex patterns can spontaneously form. But we can't really do research on these very complicated systems, so we try to find model systems that exhibit these types of growth and try to study the growth in a controlled way, trying to get really at the fundamental parameters or control parameters that lead to pattern formation. And so, as I hopefully will be able to show you, there's many, many surprises once we actually start to look into these pattern formation, which tells us already something that is very deep science behind them. And so let's just have a look again at what we just did. So you took a drop of liquid, you took your second plate, something extremely boring happens. The liquid just spread out uniformly and formed such a circular disk. Then the second part, and now you see it more clearly, you saw all these fingers invading. You got all these branching events, branch structures leading to this beautiful pattern. And so what you did actually, or what you had in these experiments, is you have two fluids. You have your drop of liquid, or your drop of fabric paint, and you have the air. And so these two liquids, or these two fluids, they have very different viscosities. But the viscosity is essentially a measure how easily a fluid flows. So your drop of dye has a much higher viscosity than the air. And so now, whenever I have two fluids of different viscosities, I'm going to get such patterns in the case where the less viscous fluid, which for us was the air, is invading the more viscous one, the drop of liquid. Where in that case, the interface between these two fluids is unstable, and you see the growth of these small perturbations into very large structures. Now, in the first part of the experiment, what you essentially did is exactly the inverse, where you had a more viscous fluid, the drop of liquid displaced the less viscous one. In that case, you don't get the instability, and small perturbations get stabilized. So the viscosity is really the control parameter for the formation of these patterns. And so what I show you here is an example of instability that we see in fluids, and it's called the viscous fingering instability, and it's characterized by these very repeated branching events. And so now in the lab, we want to study this a little bit more controlled than the experiment you just did here, but it's very similar. So we again have two plates. They are now essentially fixed with respect to each other. So they have a fixed constant gap spacing. One of these plates has a hole in the center. We can inject the fluids into this hole. It will spread out in this gap. We can then inject a second fluid and essentially watch from the top how the outer fluid will get displaced by this inner fluid. And so I'd like to show you a movie of how that looks like. Again, you have a less viscous fluid. In this case, it's dyed water that displaces a more viscous oil. Now the oil is already pumped in. I will pump in the water through this tubing, which leads to the center of the plates. And again, you see these exact same features of the pattern evolve. You see the system is unstable, so starts forming fingers. As these fingers grow, they repeatedly split, and you get these many branching generations. And so, if you look at this pattern, your eye might immediately pick out that it has all these fingers kind of have about the same width. And indeed, we can describe this width, which is essentially given by 3 control parameters. And so the 3 important parameters, one of them I already told you about, is the difference in the viscosity between my 2 fluids. Another important parameter is how quickly do I form my pattern. And the last one is what is the surface tension between my fluids. And so what this equation essentially tells you is if you look at your pattern and the pattern of the person sitting next to you, if your pattern has thinner fingers, that essentially means that you did the experiment more quickly. And so these 3 parameters, surface tension, viscosity difference, and velocity, determine the width of the fingers that you get in your final structure. And so this is essentially the picture we had of these instabilities about 3 years ago. But I'd like to show you something that surprised us a lot and that essentially told us that what I just told you now is only half of the story. And in order to do that, I'd like to show you again 2 videos. And so I'd like to show you 2 videos where I'm going to create patterns which have different finger width by essentially changing, again, how quickly I inject my fluid, so the velocity of the interface. So in the first video, I do this rather slowly. I again get these fingering patterns, the fingers split, many generations. Now in the second video, I keep everything the same. I just increase the velocity by about a factor of 10. And so if you look up here, an increase in the velocity will lead to a decrease in the width of the fingers. What this means, my fingers will become narrower and they will split much more often. So I will get a pattern that has many more branches and looks much more complex. And so we do the experiment. And what we see isn't at all what I just told you should have happened. So instead of getting a much more branched pattern, we get something that is almost completely stable and just has these tiny undulations at the interface. And so really, this is against anything we would have expected to happen. And there's really something in this picture that is missing. And so what is it? What else comes in than just these parameters that I told you up here? And so in order to find that out, we did a whole bunch of experiments where we essentially made the system even simpler and now chose systems with exactly the same finger width. But even doing that, we got a whole slew of different patterns. And so what did I actually change here, right? So the parameter that I did change in all of these experiments is the ratio between the viscosity of my inner fluid and the viscosity of my outer fluid. So if you go back to look at the wavelength, the important parameter that comes in is the difference between my 2 viscosities. But now we realize that not only the difference between the viscosities, but also the ratio between the 2 viscosities is actually a very important control parameter. And it's a control parameter which very systematically changes our patterns from a pattern with very long fingers to a pattern with shorter and shorter fingers and a larger and larger inner circle region. So this really gives us a second way of actually choosing the types of pattern that we get, or controlling the types of patterns that we get, where the viscosity ratio sets the relative length of the fingers. And so what this tells us is that there's really 2 length scales in this problem. There's the width of the fingers and the length of the fingers, and we can change them independently. And so we can learn something about these very branched patterns that lead to this somewhat random and disordered type of growth that we see over and over again in nature. But if you think about nature, nature has many more tricks. Nature, for example, can make very ordered structures. But where we get structures that have a really high symmetry, in this case, a snowflake is 6-fold symmetry, which is the ordered growth, which we call dendritic patterns. And so these dendritic patterns, again, occur repeatedly in nature, in snowflakes, in solidifying aloes, in copper oxides. So it's kind of a different design strategy for nature to make a pattern. And so what's important to get to this ordered type of growth is that in the system, there needs to be some anisotropy in the interfacial dynamics. So anisotropy is essentially a property that is directionally dependent. So in the snowflake, we can very easily understand that. So in the snowflake, what gives us the anisotropy is essentially the structure of the water molecule, which has a specific angle. And now if these water molecules, they start to form, they crystallize into an ice structure. Because of the structure of the individual water molecule, the only structure they can form is essentially this six-fold symmetric lattice of ice. And so this six-fold symmetric structure at the molecular level leads to macroscopically a growth that is six-fold symmetric. And so now I'm telling you about these fluid instabilities, and the question is, can we get such ordered structures as well in our very simple model system of fluid flow? And the answer is yes. And so we don't have any symmetry in the structure of our liquid, but we can impose a symmetry to simply the environment where these structures grow. So I can take my same plates, but now make my system directional by engraving with, for example, a laser cutter, an ordered lattice onto one of my plates. And doing that simple modification to the system leads to a completely different type of growth. So now, instead of getting these very branched and ramified patterns, what you see is now that I inject the second fluid, I get these extremely ordered structures reminiscent of these dendritic structures in nature. And so I mentioned before the importance of the viscosity ratio as a control parameter, and this still is a very important parameter, and it's important in a very somewhat interesting way. So you see, I impose here a six-fold symmetry, and I get a six-fold symmetric pattern, which makes a lot of sense. But now I still take a six-fold symmetric lattice. I take patterns at higher viscosity ratio, and now, instead of getting a six-fold symmetric pattern, I get a 12-fold symmetric pattern. So the viscosity ratio really governs the symmetry of the pattern formation, where I change from 6 branches to 6 small ones, 6 short ones, and eventually 12 branches of equal length. And so we can get, in such a simple system, models for both branching type of growth and dendritic type of growth. And the morphology selection, or which pattern the system actually chooses to make, depends on the intrinsic symmetries of the system. It depends on the growth environment. And in nature, it depends on the desired function of a material or of a system. And so we have these two extreme types of growth, branching growth, dendritic growth. But I'd like to show you a picture of a system that we also get in these instabilities, which honestly doesn't look at all like any of these branching pictures or any of these dendritic types of growth. And so what is it that we actually see here? And what we see here is really a type of growth that we have discovered in this system, which is essentially a new class of patterns that we start to see in these instabilities. And so these patterns, they occur when the viscosity of the inner fluid is about 3 to 10 times lower than the viscosity of the outer fluid. And so in this case, this is how the pattern evolves. So you see again, we form these structures very early on, and then the pattern grows. But now, it clearly doesn't make a lot of structures. So the only thing we see is essentially these very blunt features at the interface here. And clearly, these aren't fingers, so we call them the toes. And so these toes, what is really different about them is that these toes, they never split or they never branch. And so I show you here a time series of these, the video I just showed you. I can zoom in at early times. These patterns still grow at this typical width of the fingers that we would expect. But then, as they grow on, they can get very, 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 very large, where in principle they should split once they reach twice that width. But they don't. And so this really leads to a type of growth that is very different. And it's a type of growth that you are all, to some extent, familiar with. It's a type of growth that's called proportionate growth, and is essentially the way you grew up. And so what I mean by that is the moment you were born, you had a certain structure. You had a fixed number of fingers, fixed number of toes. And as you're growing up, your entire body was essentially expanding at more or less the same rate, with the exception of your head, which was growing a little bit slower. But overall, your body remained pretty much the same shape it had the moment you were born. So if I wanted to quantify that, I could have measured, when you were 5 years old, your length of your body, your length of your arm. I could have done the same experiment again at a later time, your length of the body, length of the arm. I can plot this as a function of your age. So you see both the body and the arm, they first grow rapidly, then you're in childhood, then adolescence, and eventually you're an adult and you're fully grown. Now, the interesting thing, and which is what makes your shape essentially preserved during the growth, is that if I take the ratio between the length of the arm and the length of the body, this essentially remains more or less constant throughout their entire lives. And so this is what we call proportionate growth, and this is actually a common way for mammals to grow, or animals in general. So it's very common in biology. But can you think of any system outside of biology that would grow that way? So crystals are very ordered. So they would grow by this dendritic ordered type of growth, because there's some symmetry in the crystal structure itself.
All planets are spherical?
So a spherical object is a somewhat different case, because what you need to grow by proportionate growth is at least 2 length scales that grow. So just a circle is indeed, to some extent, growing in proportion, right? But there's just one scale. So what is it growing in proportion with, right? And so if you don't know an answer, that's fine, because we don't have one either. Which essentially shows you how rare this proportionate growth is. But so what I'd like to show you is that really now we have this one system, these toes, that essentially have all the features of a system growing by proportionate growth, which is, to our knowledge, the first non-biological system, physical system, that essentially grows that way. And so what does it mean? So I can measure the same as I did for body length and length of the arm, the length of the toe and the length of this inner circular region, so 2 length scales. I take their ratio, and you see that as a function of time, except in the very beginning, but later on, this is constant, which means that the toes grow in direct proportion to this circle. Now, we have a fixed number of toes and never form any new ones because they never split. And finally, it's easiest to see that very visually, where you essentially just look at this time series again. You take the system at early times, you expand it to the size of the system at late times. I can then simply take the outline of my system at early times, print it on a transparency. So this is early times. This is at very late times. And you see that during the entire growth, the structure remains preserved. And this is remarkable because you see that not all these toes are actually the same, right? So here's a smaller one next to a larger one. But even these details of the structure remain there during the entire growth. So what this means is this is really a system that has some memory. So I can take this system, look at it at late times, and essentially know exactly how it looked at a much, much earlier time. So this is really an example of a memory formation in a fluid system, where the system remembers the initial state during its growth. But this is a very, very subtle state, because what needs to happen is essentially that I need to form a first instability in order to make these structures. Otherwise, I just get this circle. But then, once these first structures have formed, what needs to happen is essentially that this instability doesn't occur again, because otherwise I get branching. And so in order to get a memory in such a fluid system, I essentially need an instability one single time, but then any further instability would destroy that memory. And so this is really a very, very subtle situation that we see in this tow regime here. And so far, I hope I could give you a little bit of a glimpse into the world of pattern formation, showing you that we can study with these fluid instabilities 3 common growth morphologies: a branching growth, a very ordered growth, and we see this proportionate growth. So in all these systems, we could really follow their evolution. We could see at any moment in time where the system is going. But very often you encounter systems where you can't see exactly what is happening, or you can't see it very easily, but you just essentially get a snapshot of what has happened at the very end of the process. So for example, who wants to guess what you're seeing here? Blood splatter. Okay, exactly. So you see a drop of a liquid that has essentially splattered onto a surface. And so you see this and you can get some idea of what has happened to this drop, but you can't really know how this structure has evolved, how the system got to this state, because everything happens extremely quickly. However, in our lab, and this is really a different story I want to tell you about pattern formation in fluids, which is a story about a really, really familiar phenomenon, an impact of a liquid drop onto a substrate. But I'm going to show you that it's a phenomenon that completely defies our intuition. And so in our lab, we can actually study such systems in much detail because we have tools that allow us to film these droplet impacts with very, very high speed. And so what you're going to see here is essentially a drop of ethanol that is going to impact onto a dry glass down here. And in order to see that, we had to film this phenomena at 50,000 frames per second. So this happens extremely fast. And so what you're seeing here, I'm going to stop it right here, is it's coming. I just want to make sure you understand what you're seeing. So it's a drop of liquid, in this case it's ethanol. You see this bright spot here. You can ignore it. It's just optical effect because we light the drop from behind, but the drop is really this entire structure. You start to see its reflection down here, and so the substrate is right here. And so now we're ready for the impact. Commercial's over. Yes, that's absolutely right. So Edgerton could essentially, so he did very, very clever photography over 100 years ago, where you essentially could take just one snapshot of that process. And these you might all know these pictures, right? What we can do here is essentially, because we live 120 years later, film the entire process. And so what you saw here, right, is that as the drop impacts, it creates this thin sheet, this very beautiful structure, which eventually breaks up into hundreds of droplets that fly all over the place. And so if I ask you what you think might be important control parameters for how such a splash looks like, what would your guesses be?
The velocity of impact.
How fast it hits, exactly. That's definitely an important one. Viscosity, exactly. So I told you before about viscosity, so I'm going to tell you about it again. So viscosity matters. So I just showed you a drop of rather low viscosity. Now I take a drop that has a somewhat higher viscosity, about 10 times as high. And you see that the process occurs somewhat differently. So we now get still this thin feed structure, the same as we saw before, but at a very different angle. We again get the formation of droplets, but they appear to be much larger, so there's some differences depending on the viscosity of the liquid that I'm using.
How about volume?
Volume, how big the drop is, very important as well. Yes. What else? You guys are good. Temperature changes the viscosity of the fluid, and therefore it would also have an effect. Exactly. Yes. Surface. Exactly. So does it fall onto a smooth substrate or on a rough one? And so these were on smooth surfaces. Now I show you a splash on a rough substrate.
Which liquid? Oh, sorry.
Yeah, it's the same liquid as this one. So these were both 2 silicon oils of viscosity about 10 times of water. And so again, the splash looks different. So you guys are absolutely right. So we had viscosity, surface sharpness, we already found everything else. So no one tells me anything about the air. The air isn't important here.
Other liquid. Yeah, the fluid.
So angle of impact plays a small role. Exactly, so we have this second fluid, right? So, but what would this second fluid do, right? What would the air do? In principle, my first guess would have been doesn't do anything, right? Because density is much lower. But then you start thinking about it a little harder, and maybe you'll remember that if I do this, right, I feel some resistance to doing that, right? So maybe the air could prevent my droplets from really flying off very fast, very far, right? So maybe if I can do an experiment where I can take some of the air out, and by that I essentially mean lower the pressure, I will get a much bigger splash, right? So let's see. Yeah.
Is there a thin film of air trapped between the surface of the fluid drop and the glass plate below?
Fantastic question. So should I answer it now or should I wait just 2 seconds? So let me wait just a minute to answer your question. But fantastic. So, and you're going to see why I make you wait. So, okay, so where were we? So yes, we want to do this experiment, right? Because let's see if these drops fly off further. And so I just to compare, right, this is again the splash you've seen before, so a normal atmospheric pressure, so normal conditions of air. And so now we're going to take this exact same drop, but we're going to reduce the pressure to about 1/3 of atmospheric pressure. So essentially we take out some of the air, and not that much, so this is about the pressure on top of Mount Everest. And so now let's see this crazy splash. And so there's no more splash. And again, we would never, ever have expected this to happen. Because why should the air matter? And if it did, we would have expected the exact opposite effect, that we get a bigger splash, but instead, the splash totally disappears. And so these are really these surprises that we see over and over again in these systems.
You have a picture at very high air pressure?
So we never went above atmospheric pressure because Sid Nagel, who is a collaborator in all of these experiments, doesn't want us to build bombs because it can get dangerous. But what we would expect, so we would indeed get a bigger splash if we would go to higher pressures. And yeah.
But the ethanol is evaporating from the drop faster here than in the other case.
So, but evaporation rate is negligible. So all of this, I told you, we have to film this at 50,000 frames per second. So that's a negligible effect, essentially.
Have you ever patterned your glass surface, like made half of it smooth and half
Yes, yes.
right
Yes, so Andre, who you're going to see a picture of at the very end, did exactly that experiment what happens is half of your drop splashes, half of it doesn't.
Did you,
Yeah.
did you just do the splash in a vacuum chamber just to see what
So-
it might look like?
So we don't even have to go that low. So we know that it splashes, splashes. We decrease the pressure. It splashes, 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 and at some point it disappears. So if we would go even lower, it would still essentially be gone.
How about atmospheric pressure, but with a lighter, less dense gas like helium?
Yeah. So we also tried that, and it plays a little bit the role of the exact pressure we have to go to, but it doesn't. The phenomena remains the same. It's actually extremely robust. But what's that? all right. So really, the point here to make, which I guess you all got, is I take a drop, I splash it here in Santa Barbara, it will splash. I take this same liquid on top of Mount Everest and one splash. And so I already mentioned a little bit, it's an extremely robust effect. So I told you all these different splashes we can get depending on the low viscosity or high viscosity, smooth substrate, rough substrate. But the one thing they all have in common is that as I lower the pressure, the splash disappears.
What happens if you charge the water?
If we charge the water, so we haven't tried that, but I don't think charges play a role. Yeah. So we do this with all different kinds of fluids, water, oils, and.
How about if you dropped it onto a hydrophobic plate?
Yeah.
It would be very frictionless. Would it just?
Yeah. So there's interesting stuff going on, which isn't our work, but work by people in Europe. But they essentially take super hydrophobic substrate, and then they essentially see the drop fall down, then rebound. So it does change the dynamics a bit. Yeah. And okay, yes.
Have you dropped ethanol onto ethanol and observed a bounce in the middle?
Yes, so that's a different experiment, right? Where you can have essentially a liquid fall into a pool of another liquid, which again leads to beautiful splashes. You wouldn't get that effect of the air pressure in that case. So there, it's really dominated actually by the liquids, but you get similar looking structures. Yeah. And all right, so very common effect. So happening for all types of splashing. So there must be something in common to the disappearance of all these splashes. And so really what the question comes down to is, why is the air important? And what's the air actually doing? And so I wanted to wait, because what you're saying was exactly our first guess. So to essentially see if there's a film of air trapped between the substrate and the drop, such that the drop would, for example, just slide on top of that film of air and then splash, I would decrease pressure, that film might disappear, right? So a colleague of mine, you're going to see a picture in the end, did that experiment, but there's actually no persistent film of air below the drop, which essentially tells us that the air below the drop isn't the cause for this disappearance of the splash.
What happens if you do this in the space shuttle and you throw a drop at something?
Yeah. So if it would be the same mechanism. So we can, because that's essentially what gravity does for us here, right? So if we would just splash, it would change the impact velocity, but it would still be very similar. And so all right, so it's not the air below. So what we thought was maybe it's the air above the drop or around the drop that is important. And so we wanted to actually see what the air is doing. And so I'm not going to go into details of how we do it, but we can use optical techniques in order to make the air visible. And so in this video, you're again going to see a drop of liquid impacting this substrate. And now everything that you start to, that appears in gray is essentially the flows of air that are induced by this falling droplet. Oh, sorry. Now it's actually going to impact. That was just to increase, to torture the audience.
It's worse torture
I can tell you, if you ask me in the question section, yes, I will definitely tell you. Yes, it's clear in photography, yeah. And so we see this crazy dynamics going on in the air around these drops. And so let's zoom in a little bit, see a different drop where again, we see these beautiful sheets occurring. And so I show you this again and stop the video right here to point out a couple things. So what we actually see here is we see at least 3 contributions. So back here, we see the air behind the falling drop that gets put into motion as the drop falls through. We see this signal here, which is essentially the air that was just below the drop, which has to get pushed away. And we see this vortex here right at the edge of the drop that essentially travels together with the drop and eventually gets into this large-scale structure coming from the airflows behind. And so now, is this really what leads to a disappearance of the splash? That if we change these airflows, are these airflows related in any way to the fact that the splash doesn't happen at low pressures? And so, again, we try to find the control parameters that actually set these airflows. And it turns out that they're very simple. So the only things that matter for the airflows are the impact velocity, the air viscosity, and the drop size. But if we look at what actually are the parameters that set the disappearance of the splash at low pressures, they're much more complicated. And someone already made guesses that also the gas properties start to matter, right? The impact velocity, the surface tension starts to matter. The drop size starts to be important. And so given that these are really different control parameters, we can essentially rule out that the disappearance of the splash is caused by these airflows. And so to be very honest, we still don't have the full answer. And that's essentially why we need your students in order to become scientists and help us find answers to all these mysteries. Because really, there's so many more discoveries that are essentially awaiting us.
I just have a question to understand. Is that really a folded sheet of air, the way you would fold a sheet of paper?
So it's to some extent similar, yes. It's air pushed away, and then it interacts with like the stationary air around it, and that leads to this curl up of the structure.
Is it a circle in which
yeah, exactly. You essentially see a cross section through it, but this is really a donut shape, essentially. Yeah. So this would be a 3D. If we could visualize that would be a 3D structure. And I'm already running late, so what I'd like to do is show you all the people who have contributed to that work. I'd like to point out in particular our organizer of this day and the coordinator of this meeting here, Sydney Nagel, who's really a huge inspiration for everything I do. And we talked about resources, and I added that in because I just want to, very quickly, and then I'm finishing, fantastic resource for anything fluid dynamics is a fluid dynamics blog. A friend of mine is called fyfluiddynamics.com or FIFD, where Nicole Sharp essentially posts 3 times a week tiny snippets that have to do with research in fluid dynamics. Where she essentially posts some pictures. Here she discusses the motion of clouds, and she essentially reads all these scientific papers and then takes the important content and essentially, you can't even see anything. Why is that? Let's see. So I see it. So let me go back. So you have to check it out yourself. Sorry for that. So yes, FI fluid dynamics. So she takes phenomena from fluid research that is happening right now, and essentially writes a short summary of it for a very general audience, taking real research happening right now and presenting it to a very broad audience. So this could be a fantastic research for all of your classes if you want to talk about fluids. All right, so finally, what I hoped I could tell you a little bit, I could take you on this journey on like pattern formation. And I hope I could show you that pattern growth is really full of surprises. and that we are really just starting to understand the very deep and complex science that is behind the formation of patterns. Thank you very much.
Okay, great. So thank you, Irmgard, very much, and we certainly have time for some questions.
Are these patterns in any way connected to fractals?
So, very good question. These ones are. So the most branched ones that we can reach are essentially fractal patterns with a fractal dimension of about 1.78, if that tells you something. So diffusion limited aggregation. So these are, and there was a lot of research on exactly that to see if they are really closely related to these type of fractal patterns, and has been shown that indeed the ones at very, very low viscosity ratio, they are fractal-like patterns. Yeah?
Could you please finish that sentence again that's up there?
Just read it.
Complete science behind
It. We are only starting to understand the deep and complex science behind pattern formation.
scatter formation.
Pattern formation. Yeah, yeah.
So I was wondering if this was one that didn't really form the splashing pattern, and obviously you've probably looked at the air results when you're looking at forming drops. Is it?
Yeah, it gets crazy.
Like sort of surfing up on the air, and then.
So here's how it looks.
What's going on?
So I didn't show it because if we actually want to understand the airflows, we try to prevent the droplets from splashing, because if it splashes, this is what you get. And so you still see these same structures. Now you get all these striking these contributions here, right, which essentially are the wakes of these small droplets that flew off. And so, yes?
Earlier on in the talk, you showed where you made grid marks in the plate.
Mm-hmm.
So I was thinking that the grid marks actually provided some kind of a matrix structure. So is a matrix essential for proportionate pattern growth?
So the proportionate growth happens without the grid. So the grid, whenever we have the grid-like pattern, we get these ordered structures. Yeah. And then proportionate growth again happens in the smooth, so not isotropic systems, but only at a certain range of viscosity ratios. Mm.
The visual here kind of reminds me of like turbulent vortices peeling off towards a vacuum. Is there some sort of like micro vacuum forming that's pulling on this?
Yeah, so let's see, let me go back to this. Right here, right? So this is liquid that spreads out extremely quickly. And then it essentially encounters air back here, which is stationary. And so the small structure you see here is what we call a vortex structure, which is essentially exactly what you're saying. So it's a zone of low pressure because I have this rapidly moving fluid below, which creates a low pressure just on top of it. And that's exactly this small rolled up structure that you're seeing here, which is very related to the phenomena you're talking about. Yeah.
I'm having a hard time putting my question into words.
Mm-hmm.
That's a toroidal vortex, right? Does the math behind this have any application to hypersonic aircraft and how something moves through the atmosphere? You're always dealing with that.
So, yeah. So, very good question. So you get this vortex structure in all different types of situations, right? You get them, for example, here at Santa Barbara Airport, right? If you could actually visualize it, you would see every single airplane that actually starts leads behind these vortex structures. Exactly. So, and that's to me one of the fascinating things to some extent about this, right? So you all have seen droplets splashing hundreds of times a day, right? And now we actually know that each time that happens, this is what happens in the air. And to me, that changed a little bit my picture about how I think about nature, about life around me, right? If you could only see it, then, I mean, it would be even more beautiful. And so these are extremely common structures in airflows. Yeah, yeah. Sorry.
I'm struck by the symmetry of the air displaced drop, because when the drop first touches, you know, there's a time lag between the center and the edge, but yet the flatness of the air displaced thing, it just seems too symmetric. Am I missing something, or something more to the story?
So it's essentially symmetric because the drop spreads out symmetrically. So the drop hits, right, and it spreads out, and the spreading is symmetric, right, to a very good approximation. And because these flows are all governed by the spreading of the drop, they in turn become symmetric. So nothing kind of kills the symmetry, right? So if now I would do the experiment that was proposed, for example, right, have the drop fall on a tilted interface, right, then it would spread out quicker downwards than upwards a little bit, right? That would lead to an asymmetric structure of the drop, and then also an asymmetric structure of the airflows.
But it just seems the center of it should be bulging higher because the impact of the center of the drop was first, but maybe it doesn't seem that way.
Oh, so the air that was, I think what you're asking, so as the drop just falls down, right, and then the air that was actually right beneath it is what leads to this crown shape here, right? So essentially what happens, my drop comes down, and then this air gets pushed out and deflected like upwards into this crown shape. So this is the signature of what was below the drop. But again, this is symmetric because essentially it's, the drop impacts in a symmetric way.
You looked at the effect of surface roughness. Did you change the characteristic size of the roughness?
Yeah.
And then is there a, below a certain limit, you see no difference between a flat surface and
So there's actually even crazier things happening with roughness that I didn't have time to tell you about. So really what's happening is you have a very smooth substrate, it splashes. You make it a tiny bit rougher, no more splash. You make it even rougher, and you get that splash I showed you. So there's even in this roughness effect some very complicated and complex science going on. Yeah, thanks for the question.
Thank you.
So I'm just curious, that little drops that take off, I had assumed just intuitively take off the way a rubber ball bounces off a wall. But are they in fact riding cushions of air? Does it have more to do with an airplane wing than a rubber ball bouncing off a wall?
So they're actually getting off. So if you remember, let me see if I can get back to the picture. So right here. So what's happening is kind of a two-step process if you look very closely. So you first form kind of this very thin sheet of air, and then you get these droplets, and then these droplets break off because these fluids have a surface tension, right, which essentially tries to make a round-shaped droplet, right? And so eventually surface tension basically wins, makes these round-shaped drops that then separate from that sheet. And so they have some momentum because of still the dynamics of this sheet structure, and so they fly kind of outwards. So they're not really bouncing droplets, but they're really essentially just getting ejected from that thin sheet structure.
Are you modifying anything in your testing leading towards perhaps improving airflow on airplanes and eliminating the vortex? You guys playing with that aspect of this experimentation?
We are not. So there's a lot of research going on large-scale vorticity in like aerodynamics, essentially. But we personally aren't working on these aspects. Yeah. But it's a huge field of research, trying to understand what happens behind the airplanes, for example. Yeah.
Is there some kind of an impedance mismatch between the speed of the drop as it's going and the ability of the air to get out of its way?
Yeah, so I think you're pointing towards pretty much what might be the science behind all this, right? So what we think now is, let's see if I have a good picture. Difficult, but let's see, I can try to stop this video at the right time. Okay, so you see that pretty much what you're saying, right? So the drop spreads out, and then you see that there's a contact line between the spreading drop and the substrate, right? So this drop spreads out on that substrate, right? And then where most likely really the answer to this disappearance of the splash is what the air very, very close to that advancing contact line is doing. So now this is very difficult to actually access experimentally because it happens on very, very fast time scales and it happens on very small length scales. And so really getting exactly the shape and then understanding the air below that spreading interface is, I think, where the answer lies, but which is something that is very, very challenging to do in experiments. Yeah, yeah.
Okay, so at this point, I'd like to thank Irmgard again for a very fascinating talk. And we have a break now.
And the photograph.
Oh, and the photograph.